What's going on, guys? In this video we are going to see how to prove this proposition using well ordering property. First we are going to take the contradiction of this one and prove that one wrong. Then if we can prove the contradiction is wrong, it automatically means the original proposition is correct. Okay, now let's go ahead and do that. First we keep the first term and we are going to find the opposite of this one, and that's going to be the contradiction. Okay, let's go ahead and write that. Let x belongs to the integer and assume x is odd. We keep this one because this is our claim. The one that comes after then, this is our claim. This is what we have to prove. Okay, claim, claim. Okay, this is our claim. Well, let's continue. So x belongs to an integer and assume x is odd, and assume x is odd. Suppose there existent n belongs to natural number. This is the contradiction of this one. This is for all belongs to natural number. If we take the opposite, the negation of this one, that's going to be there existent n belongs to natural number, and here it's odd, so the negation is going to be even. X power n is even. Okay, now here we are going to prove this contradiction is wrong. To prove that one, what we have to do is we have to, because it's going to satisfy the well ordering property, because well ordering property says s belongs to, if x belongs to an empty set, x is not actually x not equal to an empty set, and by well ordering property there exists a minimum, or you can say smallest element. So s has a smallest element. S has a smallest element, and we are going to call that element n. So let n be the smallest element. N be the smallest element of S. Okay, here what we are going to do is, if n is smallest element, then if we can prove that this condition, the negation condition, if it's applied for the one that's less than minimum, for example, if I take n minus 1 and if I can prove that one, this one satisfy the one that less than minimum, it automatically means this one is wrong. The contradiction we took, it's wrong, so it means the original statement is correct. Okay, now that's what we are going to do here. So first we know that x is odd, mean x, the power is 1. Here it means x alone, it means x power 1. Since x power 1 is odd, since x power 1 is equal is odd, and 1 doesn't belong to the set. 1 doesn't belong to the set. So n 1 doesn't belong to the set. So n is going to be, n is not equal to 1. Okay, so n minus 1 is a natural number. We can say hence n minus 1 is natural number. Now n belongs to the set. N belongs to the set because n is the minimum number, and meaning since we know that this should satisfy for the whole set, so x power, the minimum, it has to satisfy for the minimum too. So x power n is even. X power n is even, and n minus 1 doesn't belong to the set, meaning x power n minus 1 is odd. Okay, now we are going to do something different, that is choose a comma b belongs to integer with x power n is equal to 2a. 2a means if you multiply an integer by 2, that's going to be even. Okay, and if you multiply an integer by 2 and add 1 to that, that's going to be odd. So we are going to say and x power n minus 1. Since n minus 1 doesn't belong to the set because n is the minimum element, if it's n minus 1, it's not going to be the element because it's less than the minimum. So x power n minus 1 is going to be odd because we say x power n is even, n is the minimum element, and this set is for n minus 1 is not in the set, so it should be odd. X power n minus 1 is equal to 2b plus 1. So put c is equal to a minus bx, and here we know that 2a is equal to x power n. Okay, that's what we wrote right here. 2a is equal to x power n. Then we can also write this one as x times x power n minus 1, because if you multiply you will get this one back. Then instead of x power n minus 1, we are going to replace that one, 2b plus 1, x times 2b plus 1, and then if we multiply, this is going to become 2bx plus x. Thus we can say thus x is equal to 2a, x is equal to 2a minus 2bx, x is equal to 2a minus 2bx, because if you rearrange this one, if you notice this one, 2a is equal to 2bx plus x. If you rearrange this one, you will get x is equal to 2a minus 2bx. Okay, so instead of writing like this, we can just say equal to 2c. We put another one. So here we have proved x is equal to 2c. X is equal to 2c. If you multiply another integer, like an integer by c, like 2, it's going to be even. So finally we can say, let's get rid of these things. I'm going to continue on top. So finally we can say that therefore x is even. That's a contradiction, because we look at that x power, it shouldn't be true for x power n minus 1, right? If it's happening for x power n minus 1, it means like we applied n minus 1 and got even number, but it shouldn't be even number, because for all the sets that belongs, it should happen only for the sets, but n minus 1 is out of the set and it's happening for that one too. So we can say which is a contradiction, therefore for all n belongs to natural number, x power n is odd. Finally we can write therefore for all x belongs to the integer, if x is odd, then for all n belongs to natural number, x power n is odd. Okay, finally we proved this one. That's what we want to prove. I hope you guys find this video helpful. Thanks for watching, and if you are trying to learn discrete mathematics, there are a bunch of videos in my playlist. I hope you guys watch that too, and don't forget to subscribe. See you next time.